Our next chapter in our GOB online remote learning course. We're starting with chapter 12. We're still in organic chemistry, and we're still going to be talking about hydrocarbons, only now we're going to be moving on to unsaturated hydrocarbons. So these will be our alkenes, ENE, and our alkynes, YNE. So again, here are our learning objectives. I'm going to just jump right into it. When we consider something to be an unsaturated hydrocarbon, we talked about this in chapter 11. The idea is that when we talk about layers or levels of saturation, we're talking about saturation with hydrogen, the maximum number of hydrogens that could be around a carbon. We see saturation in our alkanes, ANE, our single bound carbon chain, hydrocarbon chains. Alkenes and alkynes, as well as aromatic compounds, are not going to be saturated like alkanes are. We have a general formula for our alkenes. So just like we had a general formula for our alkanes, we do have one for our alkenes as well. So if you can remember this formula, you could be given a molecular formula for a compound and be able to describe it pretty quickly without having to draw it as either an alkane or an alkene. Now, we are going to go through each of these different types of unsaturated hydrocarbons, the different reactions, properties that go along with them, but just understand all of these are considered unsaturated. Now, obviously, the more double bonds or triple bonds or aromatic portions of a compound that it has, the more degrees of unsaturation it has. So first, how would you describe this compound? This is an alkene, ENE, because we have this double bond. So we're going to first talk about how we name alkenes. So we're going to still be using our general trend of this IUPAC naming system where we have the root and the endings. Just like with our alkanes, we're going to build off of it. We're always going to find the longest chain of carbons, right, that are joined together. We're going to give the double bond, or double bonds if there's multiple, the lowest numbers possible on the chain. When you have your chain that you're picking for your root of your name, the double bond or bonds have to be in that chain. They can't be on the side. And then lastly, we're going to add prefixes for any names that we need to. And now, instead of having ANE for our ending, we're going to have ENE for our ending to represent an alkene. So for example here, we have 3-methyl 1-butene. So we're going to go through and we're going to look. 1, 2, 3, 4 is the longest chain of carbons I can have, whether I go 1, 2, 3, 4 this way, 1, 2, 3, 4 this way, 1, 2, 3, 4 that way, it doesn't matter. 4 is my longest, so I'm going to have butene as the end of my name. So I'm going to go through and count it this way. Here's 1, 2, 3, 4. When I do that, that makes the double bond occur at the 1 to 2 carbon. Now, we don't have to write 1-2 or something like that because we understand if it's on the 1 carbon, it has to be attached to the 2 carbon. So this 1 here represents where the double bond is occurring. And then lastly, here's our prefix. If this was 1, this is 2, which means this is the 3rd carbon where my methyl group is. So 3-methyl, 1 to represent where the double bond is, butene. In our example here, we need to find the longest carbon chain that contains the double bond. So 1, 2, 3, 4, 5, 6 is our longest carbon chain. We want to try and give everything the lowest numbers possible. If I started with 1 here, 1, 2, 3, 4 would be the number I would use for my double bond. If I start with the 1 here, 1, 2, I would get the double bond on the 2 carbon, which is a more desirable place for it. So I have 2-hexene, and then for my methyl group here, which is on the 4 carbon, I have 4-methyl 2-hexene. Same things can occur with a cyclical compound. So I want to give you a moment to try and name this cyclical hexene, or excuse me, cyclical alkene. 1,4-dibromocyclopentene. So we look and we see we have a 5-membered ring, which would be a cyclopentane, but there's a double bond in it. So we now have cyclopentene. We know, like before, we want to try having the numbers as low as possible. So 1,4-dibromocyclopentene. We don't need to put a number for the double bond in here because if there's only one double bond, we know we're going to have that be at the 1 position. Can you name the following compound? So we need to find the longest chain, which in this case would be 4 carbons. 1, 2, 3, 4. We could also have 1, 2, 3, 4. That's our longest chain. We're not going to start with the 1 over here because that means we would have our double bond be on the 3 carbon instead of the 1 carbon like it can be over here. Therefore, the methyl group is on the 3 carbon, which would give us 3-methyl-1-butene. Now, what do we do when we have multiple double bonds? We're going to use the same concept that we used when we did multiple prefixes or multiple alkyl groups that were the same. Remember when we had like a trimethyl? We can have a triene, which would mean there are 3 double bonds in there. We need to indicate where all the double bonds are. So in this case, we have 1, 2, 3, 4 carbons, so it's going to be a buta, di, because we have 2 of them, ene, and we count 1 and 3 as the locations of those double bonds. In a cyclical compound, we do the same thing. It's a cyclohex structure. We have 2 double bonds, so it's going to be a diene, a cyclohexadiene, and we have them at the 1 and 3 positions. What is the name of this compound? 1,4-cyclohexadiene. If this is at the 1 position, 1, 2, 3, 4. You may be wondering, why can't I go 1, 2, 3? But remember, if it's on the 1 carbon, it has to be connected to the 2 carbon. So we have to go around in that order. We can't just say 1, 3. That wouldn't make any sense. Go ahead and name these following compounds. I encourage you to pause the video here and try naming these on your own first. So as we go through to name these, we're going to use the same IUPAC rules as we've been using. First, find your longest carbon chain. Then try and get your double bonds to be the lowest number possible. And then on top of that, you're going to add your additional alkyl groups in alphabetical order. So for this compound, our longest carbon chain is 6, so we're going to have some sort of hexa compound. We know there's double bonds, so it's going to end in ene, and I count 1, 2, 3 different double bonds. So I'm going to have some sort of hexatriene. Then in between, I need to call out where are those double bonds. They're at the 1, the 3, and the 5 carbon. So 1, 3, 5 hexatriene. The last things I need to do is count out and call and name these 2 methyl groups that haven't been added in yet. They're at the 2 and 3, so we have 2,3-dimethyl 1,3,5 hexatriene. That is a better numbering system than 4,5-dimethyl 1,3,5 hexatriene. These numbers are higher than these ones, so we're going to start with 1 over here and not 1 over here. In the second cyclical compound, we're going to do the same thing again. Whenever you have a double bond in a cyclical compound, one of those double bonds should be at the 1 position, and that will help determine your counting. So we could start here and have 1, 2, 3. So 1, 3 cyclohexadiene, because we have 2 of them, diene. Or we could start with the 1 over here. And if we count with the 1 over here, we would have 1, 2, 3. So we'd still have 1,3-cyclohexadiene in each case. But let's look at the alkyl groups around it. We could have 5-ethyl, 1-methyl. Remember, ethyl comes first because of the alphabetical order of it. Or we could have 6-ethyl, 4-methyl. In this case, 5 and 1 are lower than 6 and 4. So this is the desired name that we will use. Now, when we have these double bonds, we're going to talk a little bit about hybridization again. We talked about the sp3 hybridized orbitals when we had 4 groups around something. When we have 3 groups around something, we're going to have sp2 hybridized orbitals. And this is where we have 1 s orbital and 2 p orbitals coming together, 120 degrees. So if we know that 4 groups together is tetrahedral, 3 groups is going to be trigonal planar. So when we have a compound that is trigonal planar, it will be sp2 hybridized. So for example, here's our carbon again, let's say. And we have the S, and here's our P's. We're going to only use 1 S and 2 of the P's this time. So 3 orbitals here, we get 3 hybridized orbitals out. You might be going, well, what the heck happened with this guy over here? We still have our, right, this is carbon again. We still have 4 electrons. So 1 electron goes in each of the hybridized orbitals, and 1 electron will go in that unhybridized p orbital, the one that we didn't use. This will be used to make a double bond with. So what we have happening is, remember we had that concept of the sigma bond that we talked about in the last chapter. To get a double bond, it's a sigma bond, and then we have that unhybridized p orbital. This one also has an unhybridized p orbital, and those p orbitals overlap and give us our pi bond. So please remember, even though this looks like there's 3 bonds here, this is not. This is representing a double bond, and that's because the pi bond is shaped like a dumbbell. It's not a top or a bottom, it's this whole shape. Okay, so when this folds over, the top and bottom fold over to meet with the top and bottom of another one. We'll see what a triple bond looks like in a little bit. So in a double bond, we have 1 sigma bond and 1 pi bond. Now, just like we saw with our cyclical compounds where we had that geometric isomers, remember those cis and trans? Those happen in double bonds as well, and triple bonds. And that's because we've lost rotation between these 2 carbons because of the double bond. So we can look and say we have 2 butene in both of these cases. 1, 2, 3, 4 carbons with a double bond at the 2 carbon. 1, 2, 3, 4 carbons with a double bond at the 2 carbon. So these are both 2 butene. But they're different, right? The arrangement of them is different. They're attached the same, but their arrangement in 3D space is different. And in these cases, unlike in the cyclical compounds we're looking at on top and on bottom, now we're going to be looking at which side they are on the double bond, okay? We cannot compare on this side. What we can compare is this side versus what's happening on this side of the double bond. So in this case, the methyl groups are both on the same side on opposite ends of the double bond. We could also compare the hydrogens. So it's cis. In this case, when we look on each side of the double bond, the CH3 groups and the hydrogen groups are alternating. They're on opposite sides of the double bond. So this would be the trans. You have to look across the double bond. So how would you describe this molecule? If this is the cis, we could also have the trans of this molecule. If the CH3 was down here and the H was up here. Which of the following molecules can exhibit geometric isomerization? Now, these are slightly condensed. It's hard to see where the H's are. I would encourage you to go ahead and draw each of these out in their fully expanded Lewis structure to be able to determine which is going to have the ability to have a geometric isomer, or which ones have geometric isomerization going on. I'll pause the video here. I encourage you to stop and draw out these Lewis structures and figure it out for yourself. So, when we go through and draw our expanded Lewis structures, we know that we have the double bond, and when we have something like this top one, CH here means that there's a chlorine attached to this carbon and there's a hydrogen attached to this carbon. And the same over here, hydrogen and chlorine, which would look something like this. So, we could have this structure, but we could also alternate. This would be the cis. Here's our cis, Here's our trans. The second molecule does not have that option. It was CH2, connected to the chlorine. Because these are identical groups here, it doesn't matter if these switch. At no point will we be able to have a cis or trans here. This is it. This molecule can only be written this one way. And then lastly, for our third molecule, we have ClCH, double bound to a CH, bound to a CH3. Now, we can look at the hydrogens. We can have the hydrogens be cis across the double bond, or we can have the hydrogens be trans across the double bond. All of these have the name. I would encourage you to go back through and make sure that you can name all these compounds as well. It's really much more difficult, I find, for students to be able to look at a structure and write a name than it is to have the name and write the structure. So what are some of the physical properties of alkenes? They're very similar to alkanes, right? We know that they're only hydrogen and carbon, so they're still going to be nonpolar, which means they're still insoluble in water, okay? So alkanes and alkenes, and we'll learn alkynes as well, none of these are soluble in water. Alkenes contain 4 carbon atoms that are gases under normal conditions. Most of them will be liquids, and some of them are going to be solids. So anything with under 4 carbons will be a gas. Approximately 5 to 17 carbons in the chain will be a liquid, and anything over 18 is going to be a solid. So small ones are gases, middle-sized ones are going to be liquids, and very, very large ones will be solid. Again, these will be less dense than water, just like alkanes, so they're going to float on the water. And the low molecular weight, oftentimes these alkenes will have kind of like a gasoline-like smell to them. So here's some examples, just like we've seen before, where we can go ethene. Now notice, we can't have methane. There's no such thing as methene, M-E-T-H-E-N-E, because there has to be a double bond, and meth means only 1 carbon, so that carbon can't be double bound to anything. So the smallest alkene, E-N-E, that we can have is ethene. Ethene, propene. Now 1 butene, if we had 2 butene, it would be here. Okay, we could have 1 pentene, we could have 2 pentene, or we could have 1 or 2 pentene, right? So you need to just be able to go through, and 3 pentene, and identify where that double bond is. So we're just showing you the 1 series here. And again, we see the same trend, that as they get bigger, their boiling points and melting points get higher. So, take this time right now to give this a shot. Practice naming this compound. This is cis-3-heptene. So we need to count our longest chain of carbons. 1, 2, 3, 4, 5, 6, 7. So we know it's going to be a hept. There's a double bond, so it's going to be some sort of heptene. We need to say where the double bond is. 1, 2, third carbon is smaller than 1, 2, 3, fourth carbon. And lastly, as we look across the double bond, the hydrogens are on the same side as we look across the double bond. So this would be cis-3-heptene. How would you answer this question? They'll float on water. We know alkenes as well as alkanes are less dense than water, which means they'll float on water. This is the end of our first video for Chapter 12.